What I'm going to do now is go through several examples of computing the derivative using the chain rule. Now, this might involve chain rule with product rule or product rule with quotient rule and chain rule, but several examples. And the examples I'm going to use are on page 140 in the textbook, 140. So this is page 140 in the text. And I'm going to work through several of these even number problems, starting with problem number 10. So I'm going to work, I won't work all of them, but because that would be a 16-hour video, I think. But I will work several of these, maybe every few of these. So number 10 says I'm going to find y is equal to 5 times 2 minus x to the third. So this is number 10. Y is equal to 5 times 2 minus x to the third raised to the fourth power. So this is a quantity raised to a power. That is a dead giveaway. One of the things you're doing here is almost like the metaphor is you're learning to be a tracker in the Old West, and you're seeing some footprints, and oh, I recognize that's the bobcat, or whatever it is you're tracking. And so whenever you see quantity raised to a power, that's the chain rule. And in fact, that's the chain rule. Quantity raised to a power, that's the chain rule using the power rule because it's a quantity raised to a power. It's the power rule. And so, the derivative, we can either write this as y prime, we can write this as dy dx. And so there are several different choices. I'm going to go ahead and use the prime notation. The derivative is, if this were ordinary 5x to the fourth, it's 4 times 5. It's the exponent times the coefficient. So this is 4 times 5 is 20. Copy paste to the third power. 4 times 5 is 20. Copy paste to the third power. But whatever you copied and pasted, you multiply by the derivative of what you copied and pasted. So this is the derivative of 2 is 0. The derivative of negative x to the third is negative 3x to the second. So there's derivative for number 10. All right. Let's see. Let's play with number 14. Or how about number 16? Number 16's got a little more spine to it. So this is 2 times the fourth root right? 2 times the fourth root of, says 9 minus x squared. And again, rewrite. No calculus is happening here. I'm just rewriting because radicals don't play well with derivatives. This is 1/4 power. Fourth root means 1/4 power. And here it's the same problem, different numbers. Quantity raised to a power, that's the chain rule using the power rule. So this implies the derivative is 1/4 times 2. I'll just write 1/4 times 2 times, this is copy paste. 1/4 minus 4/4 is negative 3/4. That's a 4. Times the derivative of what was inside, negative 2x. If you want to simplify that, 2 times a fourth is a half. If you want to simplify it, that's wonderful. But if all you're asked to do is find the derivative, then you do not need to simplify. In some cases, I will explicitly tell you not to simplify. All right? Let's play with something like number 18. That's got a little something going on. So there we have those, 10 and 16. Number 18's got a little something going on here. Number 18 says, what do we have? We have s of t, 4 minus 5. It's 1 over 4 minus 5t minus t squared. All right? So we have a choice here. First, you could just, Dr. Guffey used to call this just the bulldozer technique. Just don't try to be pretty, don't try to be fancy, just bulldoze right through it. And so I'm going to use the quotient rule. one technique here is use the quotient rule. It's denominator times derivative of the numerator minus numerator times derivative of denominator all over denominator squared. It's denominator times derivative of the numerator, derivative of a constant is 0, minus numerator times derivative of the denominator, that's negative 5, minus 2t, all over denominator squared. And if you like, you may simply leave it like that, and that's wonderful. Let me show an alternate way. An alternate way is this. Rewrite the problem. See, this can be thought of that to the first power. So what we could do is rewrite the function by taking this out of the denominator, moving it to the numerator, and making the exponent negative. We could rewrite this 4 minus 5t minus t squared to the negative 1. Right? Remember, if I have 1 over x, that's the same thing as x to the negative 1. If I have 1 over stuff, that's the same thing as stuff to the negative 1. So I'm going to simply rewrite this as quantity to the negative 1. This is, I don't care which of these you pick. Just pick one and go with it. Some students love this because it avoids the quotient rule. Because this no longer has quotient rule, but it does have the chain rule. So this is now the same problem as we were doing earlier with number 10 and number 16. Multiply negative 1, copy, paste to the negative 2. Copy, paste. But then you multiply by the derivative of what was inside, which is negative 5 minus 2t. And there you go. Those, it turns out those are the same expression. It's not very hard to see those are the same thing, but they're the same expression. All right? Let's see. Let's hop on down maybe to something like number 26. Something like number 26 has a little more going on here. Because number 26 says I got y is equal to x squared it's got the square root of that says, I believe, 16 minus x squared. As usual, rewrite. Get rid of the radical. But look, now we have product rule. There's the first, there's the second. Product rule. First times derivative of the second plus second times the derivative of the first. When we do the derivative of the second, that's going to require the chain rule. So, the derivative is, and here's where it's nice, it's first times derivative of the second plus second times the derivative of the first. Just kind of line your parentheses up so you know where you're going. First, copy paste. Remember, product rule requires copy paste. First times. Now, take the derivative of that as if it were the only thing written on the board. The derivative of that is the power rule. 1/2, copy paste to the negative 1/2 times the derivative of what's inside is negative 2x. Do we follow that? Power rule, copy paste, reduce by 1 times the derivative of what was inside. First times derivative of the second. That's why it's convenient to have these, because now you, okay, where the heck am I? First, or, oh yeah, second times derivative of the first, and you're back on track. First times derivative of the second, plus second, copy, paste. Times derivative of the first, and you're out. If all you're asked to do is find the derivative, then there is no reason in the world to simplify that. In fact, just let it sit there and don't try to make anything fancy out of it. All right? So there's number 26 in all of its splendor and glory. Let's try, oh my goodness, number 30. Number 30 looks like there's no way in the world I can figure that out. Number 30 says h of t is given by a great big fraction. T squared over, good Lord, that's tiny type. T squared over t to the third plus 2, and that's raised to, I believe, the second power. All right? Quantity raised to a power. Quantity raised to the power is the chain rule. That's the power rule. So, multiply the exponent down, copy, paste, reduce by 1. Copy, paste. Times the derivative of the inside. Take the derivative of that as if it's the only thing written on the board. That is the quotient rule. So you get the hang of this. If you practice this often enough, you start to recognize, you get the rhythm. Once you get the ball rolling, it starts to kind of take care of itself. If you just keep going at it, back and forth, eventually you get success. Working with the chain rule is sometimes it's like kind of tipping over a Coke machine. You got to kind of get rocking back and forth a little bit, and then eventually it's going to go over. So just keep working at it. This is, I need the derivative of the inside, so that's the quotient rule. So that's denominator times derivative of the numerator minus numerator times derivative of denominator all over denominator squared. Denominator, copy, paste. Times derivative of the numerator minus numerator times derivative of denominator all over denominator squared. And then put a box around it like you're proud of it, and everybody's happy. So, chain rule, chain rule, chain rule. Chain rule works with product rule. Chain rule works with quotient rule. Chain rule works with chain rule. And so, if we continue on here for some of these numbers in the 30s and 40s, now we're going to throw in some trigonometry. So let's just start with an easy version. Let's start, 36. For some reason, students have problems with 36. I don't know really why, but it's just unfamiliar. So I believe it's number 36 we're going to play with. We have y is equal sine. And again, the textbook does not put, I always put my arguments in parentheses. It really helps at this stage to help see what's happening here. Treat pi as if it were just an ordinary number, because that's all it is. If this were 4x, then this is sine of stuff. The derivative is cosine of copy paste times derivative of the inside. And you're done. Well, this is the same thing, except instead of 4, you have pi. You treat pi just like you did the 4 over here. So this implies the derivative is, work from the outside in, derivative of sine of something is cosine of the something times the derivative of the something. But the derivative of the something times x, the derivative is just that coefficient. All right? So that's all there is to that. All right, let's see if we can fiddle with number 40's got a little excitement going on here. Number 40 is like, I give up. No. It's way too early in the semester for that. Wait till November, then you give up. No, I'm just kidding. We got cosecant of 1 minus 2x. 1 minus 2x quantity squared. I believe that's what we have here. Yep. All right. So this, the square does not apply to the cosecant. The square only applies to this piece, right? So work from the outside in. Work from the outside in. What's the derivative of cosecant of something? Remember, the derivative of cosecant is negative cosecant cotangent. So the derivative of cosecant of, it can be anything, is negative cosecant times cotangent of of the same thing. These and these have to be the same thing. And then you have to multiply by the derivative of that stuff. All right? So cosecant and secant are special. You have to copy and paste it twice. Copy, paste it twice for cosecant and for secant. That's a special case, which is why I wanted to make sure and do this. So the derivative of cosecant of stuff is negative cosecant of stuff, cotangent of stuff, and then you have to multiply by the derivative of the stuff. All right? In fact, I want to back this up because I want to need some more space here. This is going to get kind of big here. So y prime is, let's do it again, negative cosecant of the stuff, cotangent of the stuff, and then times the derivative of the stuff. What is the stuff? Is this junk to the second power? See, I like to go ahead and put this in parentheses, just to emphasize that. And this is copy, but you paste it twice. All right? And then you multiply by the derivative of whatever you copied and pasted. We copied and pasted this. That's what we copied and pasted. So we need to multiply by the derivative of that. But the way you find the derivative of that is the chain rule. You got to use the chain rule again. Because the derivative of this is, multiply the 2 down front, here, I just might as well write it up here, this to the first power times the derivative of the inside. You take the derivative of this as if it were the only thing on the page, which is why you slog through 10 and 12 and 14 and the 20s, so that when you get to the 30s and the 40s, you can use those skills as you build up more and more complex functions. And so this is 2 times stuff to the first times the derivative of that. So 2 times copy paste to the first power times the derivative of that, which is negative 2. And you see why this is called the chain rule, because you continue, multiply times the derivative of the inside, times the derivative of the inside, times the derivative of the inside. You continue to multiply, adding links to the chain as far as you would go. So that's got plenty to it, and that would be worth watching that a couple times to make sure we have that squared away. So what I'm going to do now is do something like number 40. This is sort of. This is sort of number 40. I'm going to say this is number 40 and a half. Okay, what if we had y is equal to, let's go tangent of, let's do x plus sine of x, that thing squared, okay? Tangent of this stuff, all right? We have a tangent on the outside. What's on the inside? On the inside, we have 2 on the outside and this on the inside. So this is going to be a couple chain rules. The derivative of tangent of stuff is secant squared of the stuff. Copy, paste. And then you multiply by the derivative of whatever you copied and pasted. This is 2. Secant squared of stuff. You multiply by the derivative of whatever you copied and pasted as if that is the only thing here. And the derivative of stuff to the second power is 2 times stuff to the first power times the derivative of the stuff. Stuff to the first power times the derivative of the stuff is 1 plus, what's the derivative of sine? Cosine, and we're out. So there's plenty there, and it just takes practice. That's all it is. It takes practice, it takes practice, it takes practice. And I think most of the rest of these are of a similar nature. So work through those, practice, be able to work the chain rule. Once you know how to find the derivatives using the basic rules, power rule, derivative of the sum, constant multiplier, those things. And once you know how to use the power rule and the quotient rule and the product rule, quotient rule, and chain rule, then with just a few exceptions, you have enough tools to find the derivative of essentially any function you've encountered in your mathematical history. There are a few exceptions, and we'll pick those up. But you have the ability now to find the derivative of almost all the functions in your experience up until now mathematically. There are a few left over. There's the exponentials, there's the logarithms, there's a few other inverse functions we have to play with. But if you can use the basic rules, if you can use the power rule, the quotient rule, and the chain rule, product, I keep saying power, the product rule, the quotient rule, and the chain rule, then you have the ability to find the derivative of essentially any function you've encountered so far, with a few exceptions that we'll pick up later on.